everybody. In this video we are going to go over an application that can be applied to a unit circle. And this has to do with rotation, particularly angular rotation and linear speed. Suppose we actually have an angle that is moving at a particular rate. Okay? If we are, then this point is going to be moving around this circle at a particular velocity, and that velocity is going to be equal to arc length divided by time. However, this angle will also be moving at a particular velocity, and that velocity is going to be the change in the angle with respect to time, and of course that angle will be in radians. That way we can relate the angular displacement to the change in the arc length. And so we have so for P we have a linear speed, which is basically the arc length divided by time, and for the angle we have an angular velocity or an angular speed, which is going to be the change in radians with respect to time. And this is basically the relationship between the two. Notice here for angular speed we have basically the change in theta with respect to time. But for linear speed, we have the change in arc length with respect to time. However, we notice here that the arc length can be written as r times theta, where theta is in radians. We can group these two together, and guess what this is? There it is. Okay, so we can make that substitution, and we have this really nifty relationship between angular velocity or angular speed and linear speed, which we will be using quite often in the next two examples. Okay, and here we go. Here is our first example. So suppose we have a point P on a circle like we just saw before, where the radius happens to be 15 inches, and that ray is rotating with an angular speed of 12 pi radians per second. And we want to find the angle generated by P in 10 seconds. Okay, well, remember, angular speed is equal to the change in angle divided by the change in time. Okay, we know what time is. That's going to be 10 seconds. So that tells us that theta is going to be angular speed times time. Now with that in mind, let's keep track of what we already know. We know that our radius is going to be 15 inches. Okay, we know that our angular velocity is pi over 12. And that has units radians per second, and sometimes units are important here. Okay, and we know that our duration is 10 seconds. We also know that theta is equal to omega times t. Omega is pi over 12 radians per second, and t is 10 seconds. Okay, now notice here I have a seconds in the numerator, seconds in the denominator, and we could treat these like variables. This is actually part of what's called unit analysis. So they will cancel, and the only units that we'll have left is radians, which kind of tells me that I'm on the right track. And what we will have here is 10 over 12 pi radians, and that will simplify to 5 over 6 pi radians. Okay, so that's the answer to our first problem. Now for the second one, we want to find the distance traveled by P along the arc. Remember that arc length is going to be equal to the radius of the circle times the angle displaced. And we already know what the angle displaced is. That's pi 6 radians. I'm sorry, 5/6 pi radians. Okay, so and we know that r is 15 inches. So we can go ahead and put those values in. We have 15 inches times 5 pi divided by 6 radians. This will reduce to 25 divided by 2 pi, and the units there will be inches. Okay, and then for our final problem, we need to figure out what the linear speed is. Well, this is the distance, okay? S is basically 25 divided by 2 pi inches. T is the time, so our speed is going to be equal to the distance traveled divided by the time it took. So that is going to be 25 over 2 pi inches divided by 10 seconds. That will give us 25 divided by 20 pi inches per second, which will be 5/4 pi inches per second. Okay? Now there's another way to compute this, because remember, it turns out velocity is also equal to r times my angular velocity, or speed is equal to r times my angular speed. All right, so once again, r is 15 inches. My angular velocity is pi over 12 radians per second, and that is going to be equal to 15 divided by 12 pi inches per second. And notice here we have a common factor of 3, and when we take those 3 out in the numerator and denominator, and if we take those 3 out, we once again have 5 divided by 4 pi inches per second. So it does indeed work out the way that we would expect. Our next problem has to deal with a chain and a pulley, or a belt and a pulley, much like probably the fan belts we have in our car. So here we have a belt that runs a pulley of radius 5 inches per centimeter. No, I'm sorry, 5 centimeters. So R is 5.00 centimeters. And here we know that the belt is moving at 120 revolutions per minute. Okay? And the first thing we want to know is what the angular speed of the pulley is in radians per second. And this right here is what we call a unit conversion problem. Now, we already know that in one revolution, or that one revolution is equal to 2 pi radians. Okay, so I could actually divide everything by that one revolution, okay? And if I do, I'm going to have that 1, like I can divide 1 rev here, and divide 1 rev here, and then that will give you the statement that 1 is equal to 2 pi radians over 1 revolution. Okay, I could play the exact same game with minutes and seconds. I know that 1 minute equals 60 seconds. Okay, I can divide both sides by 60 seconds. And what I'm doing here is I'm treating also the seconds as a variable. So the 60s cancel, the seconds cancel, and the only thing I have here is 1. And that is going to be equal to 1 minute divided by 60 seconds. And we can actually use this and this to go from 120 revolutions per minute to some number radians per second. Now, how can we do that? What we want to do is multiply this thing by 1. Okay, and I have an expression for 1 here, 1 no units, and I have expression for 1 here. If I use this, so I'm going to multiply. I can multiply this by 1 by either using this value or this value. I'm going to use this. So I'm going to multiply this by 1, or more specifically, 2 pi radians divided by 1 revolution. Okay, I'm going to multiply, and notice here that now I'm going to multiply this by 1 more time, namely using this value right here. So I'm going to multiply all of this by 1 minute divided by 60 seconds. And this is an approach called unit analysis. Now in this approach, we start with something and we multiply it by 1, but in such a way that units will cancel out. And we also treat the units like variables. For example, here I have a rev in the numerator and a rev in the denominator. They cancel out. I have minutes in the numerator here, minutes in the denominator here. They cancel out. So when I'm done, all I have are radians, which is what I want, and then seconds, which is what I'm looking for. Okay, so now to get this, so my final answer is going to be 120 times 2 pi divided by 60. So let's go ahead and do that on our calculator. That will be 120 times 2 times pi divided by 60. And that right there is my answer in radians per second. That's going to be 12.566. Now we want this at 2 decimal places. My third decimal place is larger than 5. So this is going to be equal to 12.57. Okay, now the next thing that we need to do is to find the linear speed of the belt in centimeters per second. Now remember, the linear speed, that's going to be velocity, is going to be equal to the radius of the belt times its angular velocity. So we know what the radius of the belt is, that's 5 centimeters. And we know what we know what the angular velocity of the belt is. Basically, this is going to be 5.00 centimeters times omega. Now what you will notice here is I didn't write anything down. I just repeated the omega. The question here is, which omega should you use? Should you use your answer from part A, or should you use the value in your calculator? And the answer is you should use the value in your calculator. Most students have a habit of, okay, they have this intermediate value and they're going to write it down like 12.56637, and they're going to use that. You do not want to do that. This is not the most, you want to use the most precise value you have for your intermediate calculations. And this is an intermediate calculation. Although this is the acceptable answer, this is not the number that you want to use here because you might get the wrong answer. Instead, you want to use this number right here, the number that is in your calculator. Don't need to write anything down. You just need to take advantage of the history in your calculator. So your answer is going to be 5.00 times, and then you can go and highlight this number. This is the most precise number you have available, and you don't need to write anything down to do that. Hit enter, it brings it down to your equation. Hit enter again, and that is your answer. Your answer is going to be 62.83 centimeters per second. Well, specifically, it's going to be 62.831 centimeters per second. Okay. We went around to 2 decimal places. Our third decimal place is less than 5. So this will round to 62.83 centimeters per second. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Ward, signing off.